Okay. Okay. Good afternoon. So this is my second lecture. And in the first lecture, I basically introduced the scattering technique, and then we used it on some pretty conventional type of magnetic materials. And so we were looking at spin wave excitations and kind of singlet to triplet excitations, cases in which the neutron can actually create the underlying quasi-particle. In that case, we get very specific information from neutron scattering. We're simply measuring the single particle dispersion relation. We can extract all sorts of interesting information about the interactions in the system. But these are, in a sense, really well-known types of magnetic materials. And so our objective is always to find really qualitatively new states of matter and really different types of behaviors in solids. And so in this talk, I'm going to try to direct myself towards the efforts to discover and to understand the quantum spin liquid. So this is what Lucille introduced us to in her talks. Today we heard about the Kita-Abe spin liquid, and earlier she talked about the quantum spin ice system. And in this talk, I'd like to show you some of our efforts using neutron scattering to explore these kinds of magnetic materials. And I call the talk en route to the spin liquid, but I think we're not really there yet, in fact, as you'll see. But we've made some progress, and we're quite excited about the topic still. So the talk actually has two parts to it. The first part is about entanglement and emergent quasi-particles. And we're going to talk about one-dimensional quantum magnetism as a sort of introductory example where things are under pretty good control. And then we'll move to two- and three-dimensional systems, specifically the Acadmie two-dimensional, potentially quantum spin liquid system. And then we're going to talk about quantum spin ice and the Heisenberg antiferromagnet on the Pyrochlore lattice. So it's all going to be in terms of two-dimensional and three-dimensional systems. These are systems of interacting triangles or interacting tetrahedra. And certainly they're very, very unusual and strange types of magnets, but there are specific sort of experimental challenges that I'll try to describe to you that we're still working on. The second part of the talk, which I'm not 100% sure that I'll get to, we'll see how it goes, that's going to talk about magnetism near the Mott transition. And so this is really relates back to what Giovanni's talk was about, the metal insulator transition, specifically the Mott transition. And I've been interested in what magnetism looks like when we get really close to this transition, because that's where charge is actually going from a localized or bound state in the insulator to metallic state. But you still have kind of virtual excitations present when you're close to that metal insulator transition. And that should give rise to an unusual type of magnetism that we've explored in one of the materials that Giovanni spoke about, this V203. So we'll see if we get to that. That's a picture from our trip the other day. It was a really wonderful trip. So how about that? So, okay, good. So, yeah, so we're going to start off thinking about the quantum spin liquid. And I just want to, I won't go through this very much, but this is kind of the PowerPoint picture of what we think about a resonating valence bond state, a superposition of many, many, many ways, actually Avogadro numbers of ways of engaging every single spin in a singlet. You can do it in many ways on these kinds of lattices, and so you have this quantum superposition of all of those states. And that actually is a very novel and important kind of state of matter, which is characterized by entanglement. We'll talk more about that, and it's also characterized by having fractionalized quasi-particles. And why is that? Because when I promote a singlet to a triplet, then actually, as a result of the quantum superposition that underlies the state, these two parts of the triplet can actually move apart and become independent degrees of freedom in this system. And so these are topologically connected in the sense that I can really only create them in pairs. But once I've created a pair, then they can actually move apart. They can contribute to thermal transport. And my scattering experiment becomes really qualitatively different because of this kind of failure to stay together of the two parts of the triplet once excited. So they kind of fall apart. And so I can't actually individually create the spinon. And so the scattering experiment is really completely different in terms of what we see experimentally. And I'll show you some examples of that. Good. So this is all connected to the kind of, if we step out from this picture, then this concept of entanglement seems to be really the centerpiece of what quantum materials are. And of course, this has a connection back to the foundation of quantum mechanics, when the intellectual giants were discussing this concept of whether we could actually perceive of a universe that had quantum mechanics. And eventually it was agreed, and many, many experiments have been conducted, that we actually do have the possibility of entanglement existing over very long length scales. And it's actually come out experimentally so that we now can, there's now been demonstrated entanglement over thousands of kilometers of photons. And in fact, I was quite amazed to find that telecommunication companies are already heavily into this kind of arena, in the same way that when I was many years ago at Bell Labs, they were talking about mobile. Everything was mobile. We're going to be mobile and so on. We thought it was some sort of passing fad and it wouldn't sort of happen, and now it actually has happened. And so now when you talk to people in telecommunication business, they are already putting together the pieces needed in order to do quantum communication. And that there are several aspects of it. One is proven unbreakable communication channels. Many people are interested in that. Also, there's interest in being able to transmit quantum information. This is a really interesting concept because when you transmit it, you have to destroy it. So it really is transferring the quantum information between distant locations without actually observing it, because once you observe it, it's destroyed. So all of these ideas that we've read about in the context of the EPR paradox, etc., are now really turning into reality, and it really does work. However, these tend to be pairs of particles or pairs of states that are entangled, and this works basically. But what I think we don't really know for sure yet is, does it actually work in terms of great numbers of particles? Are we able to in fact create materials where 10 to the 23 particles are actually entangled in this giant quantum superposition that we've been talking about? And I'm now addressing the possibility that basically the fact that solids involve many degrees of freedom. We have phonons in there, we have lattice defects for sure. Are these going to eventually destroy this concept? And how far can we in fact take this idea of many particle entanglement? So that's kind of the kind of broader goal that we are heading for with this work. Okay, so it's all tricky and it's kind of not really known territory yet, but in one dimension things are in pretty good order. Though not in fact ordered. So in one dimension we have Mermin-Wagner's theorem helps us and actually precludes the possibility of a long-range ordered spin state that would break a continuous degree of freedom. And so the magnetism is basically going to be quantum mechanical if it really is one-dimensional. And the very first quantum mechanical model of magnetism was Bethe's spin 1/2 chain, and it turned out to really be a very, very rich model in physics and mathematics. And the progress has been just incredible, just for a bystander to see it happening, so that now it's actually possible to calculate the 2-point correlation function for this resonating valence bond state of the Lutcher to liquid state of the spin 1/2 chain. They can really calculate exactly what the Neutron scattering spectrum should look like for this kind of system. And what it is in terms of a very crass illustration is basically a means by which every spin 1/2 degree of freedom is engaged in a singlet formation with other spins that actually can be at any distance, including very long distances, and then you do a complete superposition of these things, just very roughly speaking, but it's in specific control mathematically, this kind of object. And the excitations then become associated with breaking such a singlet, creating in the process 2 spin 1/2 spinon type degrees of freedom, which then, as a result of the quantum superposition, just like Lucille described, these now are individual particles that can move around. And so in my scattering experiment, I'm always creating pairs of these particles, and I cannot control the momentum of each of these particles with respect to the center of mass momentums. This is really a key feature. In my scattering experiment, I control momentum transfer to the material, and therefore to the pair of spin-ons, and I control the energy transfer. But I cannot dictate, which of these, the one to the left or the one to the right, should receive how much momentum. And this means that I always will get a continuum of excitations when I'm talking about making excitations that consists of pairs of particles, as in this case. So basically, this kind of picture can maybe illustrate it a bit more. In the case of magnons, I'm actually able to create a single magnon by a spin flip process. And this magnon has a specific momentum, specific energy associated with it. So I can only actually have this scattering occur in a very, constrained part of scattering phase space, specific momentum, specific energy transfer. So I just have this kind of, if it's a one-dimensional case, I just have a one-dimensional dispersion relation. And otherwise, higher dimensional plane is actually constraining the inelastic processes that are possible. So this is what I would see in a typical long-range ordered magnet. But when I have pairs of particles, I'm going to control energy transfer, and I control the overall momentum transfer. But I cannot control, the individual components of the momentum transfer. And so I'm actually going to get a continuum of excitations. Now, this continuum tends to be bounded because I'm creating, let's say I'm creating a pair of excitations. Then there's a certain threshold energy required to create two spin-ons at a given center of mass momentum transfer. And that would typically be a finite energy threshold. There's also a kind of a threshold at higher energies, though various other kind of multi-particle processes actually can continue up and are possible even at higher energy transfer. So when I do my scattering experiment, I can simply look, am I seeing a sharp branch of excitations? Then I have a single particle process, so I'm having a continuum. Then it's a multi-particle process. Now, as I will illustrate, and when we go forward, is that there are other ways that I can get continuum scattering. And so I have to be pretty careful when I see a continuum, whether I, having the jump from that to saying that I have fractionalization requires other kind of information, and I feel that it's not like a logical, tight step. On the other hand, if I do have a truly, coherent mode of excitation, then I can say that I had this some sort of a single quasi-particle excitation was carried out. And this allows me to say that I have a magnon-like quasi-particle that has defined angular momentum associated with it. Okay, so that's the scattering stuff. And then just to give an example of this in one dimension. So I said there things are under control theoretically and experimentally, actually. And here's a really nice recent paper by this group. Henrik Reuno and Martin Murgal and Mehdi Enderli were the experimentalists. And they looked at this compound, copper sulfate, hydrate of copper sulfate. And this is actually the experimental data over here. Its intensity of neutron scattering is a function of momentum and energy transfer. And you can see that here I don't have very much scattering, if at all. But then I have lots of scattering in this whole kind of umbrella-like shape. And so at a specific momentum transfer, I could transfer this amount of energy or this, and so I really have a whole spectrum. And you can actually see the spectrum here. This is momentum transfer H of 0.45, so somewhere in this place here. You can see this, these are the data points. And then the thing that's just amazing in this case is that what they've shown on the right, that's actually the exact calculation of the 2-point correlation function, this monster that we spoke about in the last lecture, containing, I think, something like 95 or more % of the content that's known to exist in that. There are some processes that are not included exactly, but most of it is included exactly. The 2 spin-on and higher number of spin-ons as well. And you can see the agreement is pretty good here. I should warn that these maps, a lot can be kind of swept under the rug when you show these kinds of data, but not so much when you show these cuts here. This is really the true thing. And with just one parameter, which would be the exchange constant, they can really very accurately describe all of these energy dependencies and momentum dependencies. So in this case, I would say that in this particular temperature range, this really is behaving to a high degree of fidelity as a quantum spin liquid. Of course, eventually when you cool this thing down, then there are some sort of additional interactions that come in and it breaks out of the spin liquid state. And I'll say a few more words about that kind of lack of stability of the quantum spin liquid for the spin 1/2 chain. Oh, yes?
What's the importance of the deuterium?
Deuterium. Okay, so basically what happens in these systems is that you need to find some way of keeping the chains apart so that they don't interact too much and become higher dimensional. So they have to put stuff in between the chains, essentially. So the materials, in order to be one-dimensional, they have to have all sorts of other chemistry in there. And in this case, what was part of what they put in is basically water, or it becomes ice when they cool it down. Now you could say, why would you not put hydrogen in? And the reason, that's kind of a neutron technical reason, is that the proton neutron interaction is associated with an 80 Barn scattering cross-section. And so basically one hydrogen atom looks like 100 copper atoms or something. It's just a huge thing, and it totally overwhelms the image. So if we had used hydrogen here, this would just be tremendously messy and so on. So this is something you have to do when you have hydrogen in your chemical structure. So then, all right, so that's the spin 1/2 chain. Oh, there are now something like, maybe 2 dozen or more materials that have this kind of physics in them. And here's another example, and it just illustrates the generality of this kind of concept. Here are data actually for a compound strontium copper O2, that where the energy scale is dramatically higher. Here we were talking about things down around 0.5 millielectron volts, so this is like 5 Kelvin, so it's really low temperature physics. I think this is probably done in a dilution fridge and so on. Then you go to this compound, and actually the energy scale instead is 0.5 an electron volt for these excitations. So it's just, it's a different exchange process. The energy scale is much larger. The physics is the same, actually. And this compound, in fact, student was asking me about thermal conductivity. This compound actually has quite interesting thermal conductivity properties because the spinons move specifically along the spin chain, so it has a very, very anisotropic thermal transport properties, and in fact, a very large thermal transport at room temperature. And just in terms of the scattering, it's pretty just amazing for us in doing the experiments. All of the energy range up to maybe 100 millielectron volt, it almost looks like just a completely sharp ridge pinned right at the wave vector transfer corresponding to the anti-ferromagnetic wave vector. But it really extends up and then eventually broadens out, and then it has this continuum scattering. And these comparisons between the experiment and theory, the statistics is not so great here, but it's pretty good here, and it really seems to work quite well. So this is just just an amazing case where we feel quite confident by the state of affairs in theory and experiment that we actually do have the one-dimensional Luttinger liquid realized in these kinds of materials. Again, when you cool down, other things eventually happen. There's kind of a freezing transition and things like that that are separate from all of this stuff. Okay, so now I want to briefly contrast this with the spin 1 chain. Okay, this is not going to be my main topic, but I want to remind you that in the case of one-dimensional magnetism, the spin quantum number is extremely important for the character of the collective state that results. So when you go to spin 1, you have a totally different inelastic neutron scattering spectrum. The energy scale is what it was for this particular material, but now you have what I would describe as really sharp coherent modes of excitation in the system. Now you might say, well, this still has some sort of width, and what's he talking about, and so on, but that's actually an experimental resolution effect, and if you gave me beam time, etc., I'd be able to find an instrument that could tighten this resolution, and I'd get a sharper and sharper mode. We really think this is resolution-limited, coherent, Magnon-like excitation. And the other thing is that here we have actually a gap in the excitation spectrum. There's an energy range here where there are no excitations available, and that's called the Helden Gap in the excitation spectrum of this compound, in this case yttrium, barium, nickel oxide. Okay, now this actually gave rise to this was predicted by Duncan Haldane in the early 80s actually, all sorts of wonderful physics that gave rise to this prediction. Real kind of chutzpah moment in the sense that everyone didn't believe that this was going to be the case, and there was all sorts of skepticism. But eventually it just came out just of the experiments as well as the numerical simulations, and indeed there is a gap. And it turned out that in this component of receiving the Nobel Prize, there's also this beautiful picture which actually illustrates the character of this state that exists for the one-dimensional spin 1 antiferromagnet. And I won't really get into so many details about it, but essentially what happens in this case is that rather than having, in the case of spin 1 half chain, I have one spin half degree of freedom and two near neighbors. And so with which one am I supposed to form the singlet? That's kind of a problem. But in the case of spin 1, the spin 1 is formed from two spin half degrees of freedom, and I have two nearest neighbors, so why not just join hands and then form singlets in that way, without breaking a symmetry at all. So the neighbor also has a hand, if you will, so you join hands and you form this wonderful picture. Now, that becomes now an isolated singlet ground state. It's a very specific state, which is distinct from other forms of singlet coverings that you could have. And in order to introduce an excitation, I have to break one of these bonds. So you have to let go of the neighbor. And that basically corresponds to promoting, I wouldn't want to scribble in this beautiful document, but this is basically you're creating this triplet out of the singlet, and that is now the gapped excitation. And then this one can now move along the spin chain, and that then gives rise to the dispersion. And this is a Magnon type excitation because it carries spin 1 relative to the ground state. So I'm able to create just one of those excitations. And that's why the excitation spectrum looks, as we'd indicated, really this sharp branch of excitation. So we should expect, when we're getting into these quantum spin liquid situations, that we should expect strong dependence on the spin quantum number, in fact. And I want to discuss some of the later examples in this, with this in mind, actually. Okay, any questions so far on this little story? Okay, I would like to say a little bit about the connection sort of to materials, because I think most of the talks and many of you are aspiring theorists, but actually materials tend to be quite complex, a lot of degrees of freedom that we are not central to the physics we're trying to do, but they impose themselves and really impact the experiments. And in the case of one-dimensional magnetism, there are always interactions between the spin chains. It's just, that's going to be the case, if something is not forbidden, it's mandatory. So since we're not forbidden from having interactions, there will be interactions between the chains. And in the case of the spin half chain, there you have a system which actually is in a kind of a critical state. And it has to do, in a sense, with the fluctuating nature of the valence bond coverage. The resonating valence bond state is actually, if you just apply a tiny little staggered field, it'll respond very strongly. You could also say that it's because of it being gapless that it has this very strong response to the symmetry breaking field. So it means that if you put two spin half chains next to each other, both of them are just on the verge of forming an antiferromagnet, and any weak interaction will eventually, at sufficiently low temperature, cause the system to go into an ordered state. And that happens, for example, in the case of potassium copper fluoride. It doesn't really impact the high energy excitations. Those are still, they look pretty much like spin-ons even in the ordered state. But if you go to sufficiently low energies, you'll find that the spin-ons in the ordered state are actually bound together, and two spin half particles then form a Magnon type excitation. And so you get additional branches in the really low energy regime, which are your spin wave type excitation. So this can all be seen experimentally, and there really is a phase transition into that state. So this we should, I would say, pretty much generally expect when we have these gapless spin liquid type states, that they are frequently going to be very prone towards the development of some form of order. Now that's different in the case of a gapful spin chain, such as the spin 1 chain. In that case, each of the chains actually has kind of a quantum rigidity to it, so it likes just to sit in that singlet state. it doesn't have, the staggered susceptibility is not infinite because there's a gap in the excitation spectrum. So if I put two chains next to each other and the interaction is sufficiently weak, it's not able to overcome that quantum rigidity of the individual chain, and you actually never get order in that system. And here's an example of that. This is a compound NENP. The susceptibility, initially it looks basically like an anti-ferromagnet, Curie-Weiss law. Then you see that this turnover has to do with the development of the Helden Gap. And you can then keep cooling the system down. This was done by a group at Gainesville, Florida. And you can see that they cool down to actually really, I think, to the certainly millikelvin, maybe even microkelvin regime, and no order was developed. However, eventually there was this Curie tail, that's typically what people call it, and that basically was understood to result from defects in the sample. Because imagine what happens if you were to leave out one of these spin 1 degrees of freedom. Then you will be left with two ends, one here and one over here, which can't reach each other. So they'll have, their arms will just be dangling like this. And those dangling spin half degrees of freedom, eventually, they're not interacting very strongly with each other, but they do respond to a magnetic field, and so you get this huge susceptibility. It's basically, it essentially is like a what's it called, paramagnetic salt or something like that. There's a really low density of spin half degrees of freedom associated with the broken chain ends in the system. So it's really distinct from the spin half case. Okay, so that was one dimension. Let's see how I'm doing for time. Okay, and now I want to then move on to higher dimensions, and I'm going to now encounter the challenge of staying away from an ordered state, as we mentioned. And so I'm going to have to go to a lattice that frustrates the development of magnetic order. And in this case, I'm going to focus on the Acadmie, and then for 3 dimensions, the EPICQUR lattice. Okay. So first, the Acadmie lattice, and well, in that case, there's probably a dozen compounds or more that people are still looking at to try to develop a model for an experimental model for a Acadmie spin half antiferromagnet. And I think one of the best examples of that is the Herbert-Smithite compound, which is shown here. This is the chemical formula, and these are the susceptibility data and the specific heat data in the inset. And this really is a remarkable compound, I'll say. I mean, I think anyone who's looked at this experimentally will say that this is kind of a one-of-a-kind material. It's not a sort of an ideal quantum spin liquid, but something rather special is going on in this compound. One way you see it is that the susceptibility is very, very bland. Here we're talking about a really concentrated system of copper spin 1/2 degrees of freedom with actually really strong interactions between these, but there's no magnetic order. In fact, no spin freezing or glass formation or anything at all is happening. It just, the susceptibility just comes up in this kind of tail-like behavior. So that's really quite unusual. There's no, bifurcation or AC or peak in the AC susceptibility, and the specific heat does not show a peak. There's no kind of phase transition into an ordered state. So a lot of things that are not there. And the question is that does that imply that there's something there, such as entanglement, spin-ons, fractionalized quasiparticles, and so on? And that's basically where the research is now operating. And I think it's going to keep going for some time. The challenge that this material has is that apart from the spin halves in the Acadmie layer, there are actually 15% of copper in these interlayers. So these were supposed to be empty. That's what kind of the ideal structure looks like, but thermodynamically, no one has figured out how to avoid approximately 15% of copper sitting in this layer. And so those are not supposed to be part of the spin liquid state, and so what are they doing? And they're probably responsible for a lot of these low temperature and low energy phenomena. I'm going to allude to that in the next part of it. So it's a material that actually can be found in mines in Chile, huge chunks of stuff that would be wonderful for a big signal, but they're quite dirty and so on, and so you have to do synthetic electrochemistry or And you can create these beautiful deuterated crystals, as Yang Li and Tianheng Han did. And so we did experiments on these in the collaboration on the MAX instrument at the NIST Center for Neutron Research that I might have described the other day. And this is what you see. So here's the structure. Here is neutron scattering intensity as a function of momentum in the Acadmie layer. So it's a two-dimensional layer, so I've got 2 dimensions of momentum. And then I have 3 different energy transfer points, 7.5, 2, and 6 millielectron volts. And this is basically what comes out. It's really very strange. I mean, this was honestly the first time we'd seen anything like that. It also was almost one of the very first experiments we did on the instrument. So it's a little kind of weird, but it turned out that the instrument was very well suited for this experiment. And what's unusual is that this is the Brillouin Zone, these honeycomb regions, that's the Brillouin Zone. So in a system that would have long-range magnetic order, spin wave excitations, etc., you would basically have dispersion relations emanating from magnetic reciprocal lattice points, and there would be little rings as you come up in frequency, little rings that would replicate in each Brillouin Zone. And then you'd find your dispersion relation, etc. But instead we have these very, very broad structures in momentum space. They're quite well defined, but very broad and extending much beyond the Brillouin Zone. Now, things that are big in momentum space are small in real space. So what this is telling us is that the excitations somehow have to do with disrupting, maybe creating some sort of singlet to triplet excitation locally between nearest neighbor atoms, for example. And it turns out that if you calculate the structure factor for that kind of excitation, recognizing that you have bonds in this lattice which are oriented in 3 different ways, then you actually will generate this particular pattern in momentum space. So somehow it looks as if I'm just breaking individual singlet bonds on the lattice. But that picture cannot be correct, exactly as I stated it, because if that was all that was going on, then there should just be a sharp excitation at a specific energy transfer. But we are actually seeing this pattern persisting, both at 0.7 millivolt, 2 millivolts, 6 millivolt, and just keeps going up in energy. So there's no kind of connection between this very simple picture and what's actually seen experimentally. There's a whole continuum of excitations. You can actually see it if you map the intensity versus momentum and energy transfer, walking through the zone. Then you can actually get just a whole kind of wall of intensity coming up here. And this feature here has to do with crossing this region here. It just comes screaming up, and it's not at all fixed at a certain energy transfer. So as I mentioned in the beginning, to generate a continuum, the way we can see that happening is if it's a multi-particle excitation. And so the picture that basically comes to mind is that of a Acadmie lattice covered with singlets. So every spin is part of forming a singlet, but except for some sites which have a spin-on type quasi-particle which can move through this quantum superposition as an individual particle. And so now the magnetic excitation I could do with neutrons would be to create a pair of such spin-on type excitations, and then they can move apart. That would give me my continuum, and breaking the singlet would give me my momentum dependence. And so in fact, this is work by Oleg Chernyshov, my colleague at Johns Hopkins University, and he went and calculated the excitation spectrum actually before we did the experiment. And so we actually were able to confirm what was predicted. Now, there are various problems that still remain, and a lot that we don't understand about this kind of excitations. And one of them is, if you remember from the beginning, I said that in a multi-particle excitation, I would have a lower threshold, a certain amount of energy required to create these 2 quasi-particles. It costs energy to create it, and depending on my center of mass momentum, this threshold will actually vary through momentum space. But actually, at every momentum transfer where we see excitations, it seems to just come all the way down to almost 0 energy. So somehow it seems that we're losing track of momentum, even center of mass momentum in the process. And in this paper, which actually was eventually published in maybe Science Reports or in a very nice journal, they actually proposed a possible explanation for this, which is that the Vison, which is part of their idea for a spin liquid on the Acadmie Lattice, can serve as a source and sink of momentum. So the spinons that you create interact with the Vison, and that actually kind of scrambles momentum in such a way that you don't even have control of the center of mass momentum of the pair of spinons that you've created. And they specifically could adjust the coupling between Visons and spinons and actually cause the spectrums sort of completely just sink down and collapse. But here's the difference between this work and the work that we did on the spin-half chains. For spin-half chains, there's a completely solid theoretical and mathematical background for what the excitation should look like using neutron scattering. Here, one of the top theoretical groups in the country is not able to calculate the dynamic two-point correlation function, and there's a lot of, thought going into whether, how should this actually be done, and this is just one of the possible ways that it could be done, and it actually excludes a lot of very important additional interactions, such as the Dzieciolowski-Maria interaction. So a lot is missing, but this is a very interesting possible way that one can understand the absence of this lower threshold in the spinon excitation spectrum. I think I want to leave the Acadmie Lattice there, but I'll take any questions that you might have on it. Yes?
Yeah. So could you just say a word about how these, I must have missed this.
Yeah.
How are these actually calculated, these structure factors?
I probably would have to pretty much defer to the paper.
Okay.
I'm not sure I could. I think it's. Oh, he's gone to sleep. Okay. I think he probably. But it basically, I think this is sort of large N work. With yes, yeah. Swinger boson. Yes, it's really cool work actually, and we're very pleased that they addressed the error. But it's a complicated story. Any other questions? Yes.
Yeah, just an experimental question. Maybe how do you disentangle the response for the defect copper?
Okay, yeah, that is a very interesting topic, and basically, so this kind of project requires all experimental probes that need to be looked at. They each provide a piece of information, and NMR has been extremely important because it's possible to measure specifically, by choosing the appropriate NMR site, you can measure specific components of the susceptibility. It's a really elegant technique. So it sort of lives in real space, and it can then be complemented by neutron experiments which really live in reciprocal space. So everything we do is in reciprocal space. And so we were able, after, in fact, the NMR experiments, to kind of disentangle things in the following way. So what's shown here is our measurements, again, of the momentum dependence of the scattering at an energy of 1.3 millielectron volts. So that's what it looks like at that energy. And this feature here is this kind of honeycomb type or hexagon with the pointed end pointing upwards. And that's as I had shown you in the previous graphs. What I've shown you down here that wasn't in the previous graph is the momentum dependence of the scattering with the in-plane momentum and the perpendicular to the plane momentum shown. And what's important here is that there's no dependence of the scattering on momentum perpendicular to the Acadmie plane. That's what you should expect when you have a quasi-two-dimensional magnetic material. So then the planes are not talking to each other at all, and there can be no momentum dependence in the L direction. So this kind of scattering, we see it at higher energies, and we believe that that actually arises from the individual Acadmie layers. Okay, now why am I showing all this? Because I'm now going to reduce the energy transfer from 1.3 to 0.4 millielectron volts. And this was basically having looked at the NMR work that says what the energy scale for this gap was. We thought we'd better look at energies below this kind of gap range. And then we see this, which is actually quite different. So if you look very carefully at this sketch, here the point is sort of upwards But here, if you look with loving eyes, you'll see that this is actually the flat part is here, and the points are rotated by 30 degrees. So this whole pattern is actually rotated. It's a little fuzzy and so on, but I think we could convince ourselves that it has rotated. And then even more, strikingly, now there's very strong momentum dependence along the L direction of the scattering. It was just a straight line, and then once you go low in energy, it becomes strongly modulated along the L direction. So our interpretation is that this is kind of a threshold energy below which the scattering now involves these interlayer sites. And to sort of pin that down more, we did a modeling exercise, or some modeling was brought into it. And it turns out that if you calculate the momentum dependence of the singlet to triplet excitation involving just this pair of spins on neighboring interlayers. So this is the layer that was supposed to be non-magnetic. There's the Acadmie layer, and then there's another layer supposed to be non-magnetic. But in this case, there was actually a copper spin and a copper spin sitting sort of back to back in this way. If you calculate the structure factor for all of those kinds of pairs, then you get this pattern, which looks enough like what we measure to convince us that now we are actually making singlet to triplet excitations involving these kinds of pairs. And we didn't know that this was the kind of relevant pair that was going to exist in these layers. But this brings in, I think, a very interesting kind of perspective on the overall character of this material, including these defect spins. Because had it been for almost any other magnetic material, if I imagine having these big layers of copper spins, and then I add this disorder, I would expect to get some sort of a spin glass coming out of that. But in this case, you don't get a spin glass, and I think that the reason is that there's actually a gap in the excitation spectrum for these layers so that they cannot actually transmit the interactions between these sites. So the interactions only, you could say, is this transmitting the interaction? But this is a copper oxygen copper type interaction. That one is apparently strong, but the interaction in this direction is apparently not strong enough to, in fact, give rise to a percolating, glassy magnetism in the system. So yeah, I think by looking in momentum space, we found that actually the really low energy sector is associated with these kinds of excitations in the system. And I think it points to kind of a finite excitation energy for the Acadmie layer. But this is quite a long discussion. I think the gap has come and gone and so on, and I'm not quite sure where it stands now, but I think there's various, it's just a very complicated topic, actually. Also, the theorists are not sure whether there should be a gap or not. So that's the Acadmie layer. Okay, all right, good. So see, I'm 5 o'clock. That's so about half an hour. Okay, good. So let's, a little bit more, yeah. So then we go to 3 dimensions. Okay, so then we have to get to the EPICQUR lattice. Most other things will eventually order magnetically. And again, Lucille described this. This is the Ising case. And the basic idea is that I can have this manifold of states satisfying the 2-in, 2-out condition. It's a massive manifold having the Pauling entropy. And then I can flip a spin relative to that manifold, and that creates kind of another set of states which are, at an elevated energy because I put some energy in to create to flip the spin. But then again, I can have these monopolar degrees of freedom then move around through the lattice, as indicated in this kind of sketch here. So I'm going to look first at the classical case as kind of to get us going, and then I would like to look at a system where we can expect to have quantum dynamics. So this refers to Lucille's lecture from I think it's from yesterday, which talked about the quantum spin ice. So this is where you actually give quantum dynamics to the flipping of spins, and then you can expect to have various kinds of quantum spin liquid type states be possible. So first, for the classical case, I just want to show these beautiful neutron scattering data from Fennell et al. 2009, and they show the wave vector dependence of magnetic neutron scattering from this kind of manifold of states. So this is actually, I think it's dysprosium titanate in this case. And there are a couple of additional details about how they did this experiment. They had to use polarized neutrons to get this kind of image. But basically, this is what it looks like to have a manifold of states of spin. So imagine that the only thing I know is that there are 2 pointing in and 2 pointing out of each tetrahedron, but otherwise there's no kind of periodicity in the system. There's not a long-range order or anything. And that's why they don't see any Bragg peaks at all. In fact, there's no kind of sharp features in the data. What you see are just these extended regions where there's intensity. And this can actually be calculated. You could imagine setting up this kind of, by Monte Carlo, for example, this 2-in, 2-out state, calculating the Fourier transform, and then you get this particular pattern. So it's very well understood, and these data really do show that we have this manifold of state for a compound such as dysprosium titanate. Now, one thing to notice is that we've got these very sharp regions here coming across. This is really a very sharp ridge of intensity, and this group actually did scans across this ridge and then found as they cooled down that they got a kind of a sharper and sharper peak coming out of that. And as this peak gets sharper and sharper, there's a correlation length that you can infer from that, which is the inverse width. And this correlation length is just going off the charts, essentially. Going off the charts is maybe a bit much to say, but it's getting pretty sharp, and it goes beyond 200 angstrom, actually. So you can say, what is that length scale? And one way to describe it is that you could say it's the distance between tetrahedra that violate the 2-in, 2-out condition. When you violate the condition, that's when you have effectively a monopole in that tetrahedron. So this is essentially is telling us that the spacing between monopoles is just increasing as the monopole density is decreasing. So this is a measurement essentially of the monopole density as a function of time. So they eventually kind of annihilate, and we get into a state that has fewer and fewer monopoles in it. So a lot of the subsequent slides that you'll see will be looking at the quantum spin ice case, but paying special attention to these kinds of features. But really the most beautiful image of the spin ice manifold is in these classical spin systems, as shown here. But for the physics, we'd like to look at the quantum dynamics, and this requires us to go to a different rare earth ion. So it's still going to have the Ising anisotropy, but we want it to be a spin degree of freedom which has quantum dynamics. And that was what Lucille was talking about. Her Hamiltonian actually can execute a spin flip, and so it can describe the quantum fluctuations associated with the spin ice state. This is completely different from something like dysprosium titanate, because there the Ising spin is actually a plus minus J state. So it's really as aligned along the z-axis as it can be, or anti-aligned. So it's basically got these two states in the low energy crystal field manifold. And the Hamiltonian that we write down to think about the energetics of classical spin ice, maybe with dipole interactions and some exchange interaction, it actually will not be able to execute a spin flip. If you subject the spin ice manifold to that Hamiltonian and then project onto the ground state crystal field manifold again, then you'll just be back in the same state. So it's actually, all of the dynamics is of a kind that we're not able to describe using our Hamiltonian at all. So it's a different kind of system. In this case, on the other hand, because of the nature of the crystal field ground state doublet, we actually do have a Hamiltonian that can that will give rise to quantum fluctuations. And that has a very strong impact on the scattering experiments, because if you think about looking at a system like dysprosium titanate at low temperatures, I shouldn't actually expect to have any inelastic scattering at all. I should just have elastic scattering. So this beautiful image you saw here should specifically be elastic scattering. And so now we're interested in materials where we in fact do have quantum dynamics, and that will then mean that we'll have inelastic scattering in those systems at very low temperatures. Okay, so this is quite recent work, so I wanted to show the people that were involved in this, which was Jiajia Wen and Huiyuan Man. She's a postdoc, he's a student. he was a student, now he's been at Stanford for a while, and at SLAC. And then Seth Copier, Satoru Nakatsuji, and Tara McQueen, who did tremendous amount of effort to try to understand the crystal structure and the chemistry of this praseodymium zirconate material. And so this is work that typically does have to have very close connection between theory, spectroscopy, chemistry, material science, and so on. All of these things come in. And there are a couple of new things I wanted to mention. So this is actually quite old stuff, but there will be some nicer new stuff that I want to show. What's shown here is the elastic scattering, actually, or at least things less than 0.2 millielectron volts at low temperatures. And you see a pattern which is somewhat akin to what you saw previously. But there's some, flies in the ointment and so on, which has to do with the fact that we've gone to lower spin, so the scattering is dramatically weaker in this case, and so various issues pop up. But we have these kind of pinch point-like regions, and it looks a little bit like spin ice, so we think this indicates a 2-in, 2-out type spin condition on the tetrahedra. However, when you go to higher energy transfer and specifically look at the inelastic scattering, you find that these regions actually kind of get filled out. So these become just like some sort of starfish type shape, but now it doesn't really get narrow at these points. And so this was the indication to us that when we provide energy to the system in the scattering process, we access states which are no longer satisfying this 2-in, 2-out condition. So in a sense, it seems consistent with the classical picture would be flipping a spin and creating monopolar degrees of freedom. But in reality, it's probably a significantly more complicated situation. I was not going to get into all aspects of that discussion. But I wanted to talk a bit about the impact of defects in this crystal structure. And it turns out that praseodymium is an ion whose ground state doublet degeneracy is not protected by time reversal symmetry. It's a non-Kramers ion, which means that if the point group symmetry changes, then you will actually lift, if the symmetry is lowered, you'll lift that degeneracy. So it means that the defects in the crystal structure can kind of act like a transverse field on this effective spin half degree of freedom. So this is kind of a complexity of the system. But somehow we got ourselves into studying this material, and we had quite a bit of fun with it, but it certainly is quite complicated because of this interaction between the crystal structure and the magnetism. And you can actually detect this kind of there's another part of it, which is that it turns out that this pyrochlore crystal structure has a certain kind of instability called a beta cristobalite distortion, which I've indicated here, or Tyrell has indicated here, where each of the tetrahedron rotates a bit with respect to its neighbor. And that actually lowers the symmetry at the praseodymium site and therefore introduces a splitting of that doublet degeneracy. So it kind of drives the systems into a singlet ground state, local singlet ground state system. Okay, so then it turns out that you can control how much of this cristobalite distortion you get by the way you synthesize the sample. And so if you put extra praseodymium in, you can somehow reduce the amplitude of this distortion and therefore bring the system into a state where you're closer to having a doublet degeneracy on every side of the praseodymium lattice. And so we decided to look at this class of compounds where there's a little bit of excess praseodymium in the synthesis phase. And in NQR, you can actually see that there's a sharper defining of the point group symmetry in this zirconium NQR spectrum. So we took a look at those crystals, and we decided to use a very high resolution instrument, which is at the spallation neutron source, to look all the way down to 3.5 microelectron volt resolution. Though you'll notice previously we were looking at a half an electron volt in strontium copper oxide. So this is really, 5 or 6 orders of magnitude down in energy, actually. And still you can do neutron experiments. Now, how is that possible? It's possible using something called a backscattering spectrometer. And so what this is here's the beam coming in. The sample will be here in its dilution fridge and all this stuff. And then there is the wall is completely covered with silicon 111 single crystals. These are these kind of hexagonal shapes. And they've been set up so that the neutrons will hit the sample, scatter, maybe creating monopoles or what have you. And then they will scatter towards this analyzer bank, and then they'll scatter back to the sample, or back towards the sample where there's a set of detectors which will now detect those neutrons. So they take a round trip to this wall, but they can only come back again if their energy is exactly right. And the reason it works, sketched here, is basically that the energy resolution is related to the momentum length resolution. And you can, in normal ways, you can write down the spread in K, which has two contributions: a spread in angular space, because there'll be a spread in the angle of incidence on this crystal, and there may be some strain in this crystal, which will give rise to a delta tau. Now, in backscattering, theta is equal to pi half, and this term actually goes completely away, and you're left with delta E, which is just 2 times the energy of the neutron multiplied by the relative strain in the crystal, or just the strain in the crystal itself. So if you can have really, really high quality crystals, you can really get to very, very high resolution. So that's how they got to 3.5 microelectron volts. And then this is what you actually see in the data using this ultra high resolution. So as you cool down, and actually I should say that here we've subtracted, I think it was 20 Kelvin data as a background. Then what you see is a build-up of intensity at an energy around 0.2 millielectron volts, and then also something's happening down at really low energies. Okay, so this build-up of intensity basically is associated with the energy required I would say to create excitations that violate this 2-in, 2-out condition. And actually, it turns out that energy is pretty close to the exchange energy, the nearest neighbor exchange energy. But then, in addition to that, and now we've become pretty firm on this, you have, in fact, the development of an elastic component and some other stuff at really low energies. So now I'm going to zoom in more on the same data, and you can see, there's this kind of pseudo gap that develops towards the excitation of the monopolar degrees of freedom. But then there's also really intensity in the elastic line. And we've done the background subtraction, so we know this is actually truly elastic scattering. On the negative energy side, as I mentioned previously, since I'm at low temperatures, this goes away completely, as it should. So all of this means it's a quantum fluctuating spin system, but this means that there's also a static component. And actually here in the inset, you can see the development of this peak at the elastic line. And then there's also a really low energy component in the inelastic scattering that we can see directly in the data. Now, from there to actually having an interpretation of what all of these things mean is quite challenging, specifically because in this case, in the experiment, we don't have momentum resolution. So this is kind of momentum averaged data, and we're on our way to do other experiments where we will resolve momentum. But this is interesting in the context of thermal transport data that were measured on the same kind of samples and was interpreted as being associated with the photon excitation in spin ice. So this, in principle, this feature could be, I believe, is probably associated with that thermal transport data. It lies in the correct energy range. But having this elastic component, I think, opens up the possibility that this is actually a kind of a spin wave type excitation on top of an otherwise frozen state. So this material is complicated. There's actually a range of materials as you change the praseodymium concentration, and eventually there's some elastic component that shows up in the excitation spectrum. So any questions on this quantum spin ice type story? Okay, so sure. So it really is a question of, okay, so, all right. Okay, so I don't know how to turn on the light, but the basically elastic scattering is truly at energy equals to 0. But to be specific on that point, then in order to think about measurement, let's say of the mean value of the magnetization, maybe I'll take it squared, to really access the truly frozen part of that, then you could say, well, I should just look at S of Q. Maybe I'll put a Q on this. Maybe I'll put a Q on this one. And then I'll also have frequency, but I'll put it equals to 0. But that's not a healthy definition because I'm doing an experiment, so I have a certain resolution involved. So instead, I should be looking at S, Q, and omega, but then maybe integrated from some minus epsilon to epsilon. If I'm still kind of doing the mathematics of it, then I would like to do lim for epsilon going to 0 plus. So I want to just take a little integral in there. So it's fine that I could have scattering at energy equals to 0, but I only call it really elastic scattering, if associated with a time, an infinite time averaged moment, only if it actually takes the form of so that it has an average of an infinitesimal small interval, which means that I really only acknowledge it as being elastic scattering if it takes the form of a delta function in omega. So then it would be elastic. And whatever thing I see in front of here becomes a measure of the strength of whatever it is that's frozen. So in this case, I'm aware of I know technically what the energy resolution of my instrument looks like, and I'm getting this peak which follows the known energy resolution of the instrument. So that means that I must have a delta function potentially, but it could be broadened up to what the resolution is. And in this case, we've been working for many years on these kind of things, and usually they say, well, your resolution was so bad, you can't really, it's not really serious. But now with this instrument, this is micro electron volt, so this is in the sort of, this is really in the 10 or hundreds of megahertz range, so this is seriously frozen stuff. And now we have a statement that's interesting. Yes?
Is this consistent with what we expect for a photon spectral wave integrated over Q? I mean, as Lucy was telling us the other day, one of the key properties of the photon spectral wave is that it kind of vanishes at low energy.
Yes. Yeah.
So if you integrate over Q, is this consistent with, maybe there's a very, very low energy scale?
Yeah, that's a good question. What I'd say is that the energy scale of this feature here is actually roughly consistent with various estimates for the transverse exchange. She had this, I think it was J perp to the third power cubed divided by J squared. Yeah. So this actually has more or less that energy scale, but that is not really a hard statement actually. So I think that this could equally well be some sort of helper in Sassler.
Is that energy scale already in micro-electron volts? Is that energy scale already in the micro-electron volts?
Yeah. So you remember the transport data was sort of in the 100 millikelvin range that it was turning on, and this is that kind of energy scale as well. But so I'm not, we're not really. What I think we can say is that whatever that thermal transport is, it's somehow related to 4f electron excitations, as opposed to nuclear spin processes, which could also have had a role. But because we see this, and we can actually say that it's not a nuclear low energy excitation. It really is a 4f electron excitation. So there is actually quantum dynamics in that temperature range, but exactly what that is, we're not able to commit to, let's say, photons as opposed to some form of a glassy spin wave type excitation. So, well, let's see, how are we doing? 5:20. So how am I doing for time? Exhausted. 15 minutes. Okay. Okay. All right. So this was the quantum spin ice story. Now we have various options, and I could talk about the. I think I could talk about the antiferromagnetic antiferromagnet on Acadmie Lattice, but I'm actually more disposed towards calling this closed in terms of my discussion of the spin liquid, and I would like to say a few words about what we've been doing on V2O3. So the story there is that we're not quite there. We've got, in terms of the spin liquids, but I feel that there's a lot of progress specifically in terms of the variety of materials that people are looking at and the range of tools that they're applying towards understanding the solid state entanglement. And then I'd like to turn to the topic of V2O3. So this relates to Giovanni's talk, and actually one of the things that he was pointing out, that he was starting from high energies and looking at this. This is actually, I think, from quite an old paper, but it's one I really enjoyed reading. And so he was looking at this transition from a metal to insulator as a function of the on-site repulsion over the bandwidth of the system, and that there's a possibility of a critical endpoint and a phase transition from the metal to the insulator. So this is a beautiful theoretical concept. It turns out that it's very difficult to find materials that actually expose this line, I would say. There certainly are some materials, but it's really quite limited. And we set ourselves the question is, why is that? If this seems to be something that it seems natural that it should exist in materials, but somehow it's very difficult to find actual experimental examples. One of the few examples that does exist is V2O3, also mentioned in Giovanni's talk. And there you do have this, this is actually a first order phase boundary between a paramagnetic insulator and a paramagnetic metal. And the crystal structure is maintained. So it really is the character that we expect for the so-called Mott transition. It's not a Slater transition, it really should be a Mott transition. Now, you can see what is it that allows the experimenters to move across this phase boundary. Well, it turns out to be actually chemical doping. So this is not temperature, and it's not it's not actually pressure, because the pure V2O3 compound is already in the metallic state. So I'm not able to have less than zero pressure actually, and so what is done then is to introduce chromium to effectively increase the on-site repulsion, or introduce titanium to decrease the on-site repulsion. Then I can move across this boundary. So that's certainly a lot of additional complexity there, and there have been some recent papers really trying to understand. This was DFT work by Valenti, and I think Mila was involved as well, maybe Marzin. And so it is a more complicated story. But we were interested in how is it that this compound is somehow able to expose this line. It's not until lower temperatures that you fall into this antiferromagnetic insulating state, which somehow persists without any apparent phase boundary within it. It seems to be the same structure. And then eventually I just break out into the metallic state. So in most compounds that we're aware of, basically this line doesn't really exist at all, and I just go from some sort of metal or bad metal directly into the antiferromagnetic insulator, and then eventually at high pressure I can maybe drive that antiferromagnet to zero critical temperature, but I seldom actually see this line. So why do we have it? Okay. The experimental evidence for it is actually a doping series. These are wonderful papers back from when I was a little kid, basically. So putting in chromium, you can really increase the resistivity by multiple orders of magnitude. It really is a marked thermodynamic feature, but you need to dope, and it's a whole sequence of samples. Okay, so we wanted to understand the nature of the state. And this is quite recent work, so I just wanted to show the young people that were involved in this, which was John Leiner, who's on his way to PSI, actually, if some of you are from PSI, so he will soon be there, and Zhu Zhang, who's a student who has just graduated and is going to UCLA. And the work is in this paper, and we also thank our funding and the SNS where we did the work. So what we did was we did inelastic scattering in this paramagnetic insulating state. And I'm just showing you a bit of the data, but the message is that we have extremely broad features in momentum space. So, we were looking at the spin ice compound where we had this manifold of states. So now we're looking in the paramagnetic insulating state near the mod insulator transition, and we find really broad features. In fact, it looks just like a highly frustrated magnet of some kind. That was what sprung to mind when we saw this. So that's curious because we are really close to the phase transition into the antiferromagnetic insulating state. And so we were puzzled by why the correlation length is so short in the system. Also, the bandwidth for these excitations is quite high. So it's not as if there are no interactions. It's just that it's not able to build up correlations. So we wanted to understand why that was. And so there's a situation we don't really know the exchange constants, and we don't have a method to directly measure those. We cannot put a giant field on to drive it into a ferromagnetic state. So what we did was that we spoke to Rosa Valenti and her group, and Harold Jeschke, who was working on this, and they actually now have the capability of calculating these exchange constants, even in materials that are close to the mod transition. They are able to do this with some. I think we, in our work, can actually see that it works. It functions pretty well. So these are the exchange constants they calculate, and then we take those exchange constants. Actually, we take all of the exchange constants they calculate, and then we use something called a self-consistent Gaussian approximation to calculate the spin correlations that you'd expect with those interactions. And so this is the measurement, and this is then the calculated dynamic correlations that you would somehow expect based on these DFT results. So it's kind of quasi-ab initio, not ab initio because U was put in by hand, and also because we had to use this approximation. This approximation should be okay because we are working at very, very short correlation lengths. So somehow it actually can account for the data quite well. And so there's something frustrating in this structure. So now let's see what happens when we cool it down into the antiferromagnetic insulating states. This is at 205 Kelvin, and then we cool down to, I think it's 180 Kelvin, 170 Kelvin, and then all of this kind of collapses into really sharp, in fact, resolution-limited features in the momentum dependence, and eventually you cool to lower temperature. Some of the diffuse scattering goes away, and you have really sharp features. Now, these are actually basically what you see when you cut through a dispersion relation. So this is an ordered antiferromagnet. It has magnon excitations. I'm cutting through it a specific energy transfer. I think it's 10 millielectron volts. And these should actually be little rings, but I'm not fully resolving it. So I'm basically going directly into a really nice, coherent, ordered antiferromagnet from this very, very diffuse fluctuating magnet that I have in the paramagnetic insulating state. Okay, this actually persists over a very broad range of energies. So this is the whole spectrum as a function of Q and energy transfer in the paramagnetic insulating state. So you see these broad features, not dissimilar, in fact, from what we see in these quantum spin liquid-like materials. They tend to have really broad blobs of intensity, if you will. Similar kind of stuff is what we're seeing. You now cool it down into the antiferromagnetic state, and from this morass, basically, you have the development of the coherent spin wave modes of excitation. And actually, then you can do something else. You can, again, Rosa Valenti also looked at the exchange interactions in that now monoclinic state, so using the same method of DFT, and then taking those exchange constants, we calculate the spin wave excitations, and you get this kind of pattern. So not so bad. It's not quite ideal. The bandwidth is not quite right, and so on. But I still feel it's really impressive that that's possible to get to that point. You can then adjust the exchange constants a little to try to improve the agreement with the measured excitations, and you get this kind of pattern. And from that, you now have a set of exchange constants, and these are the Neutron-determined exchange constants. This is a really complicated crystal structure. You have to look at it for like some months or something. So I'm sorry, but you basically have a set of exchange constants, and what you find is that in that ordered state, every single pair of spins which is, let's say, ferromagnetically correlated like these two, they have a ferromagnetic exchange interaction. And every single pair of spins which is anti-ferromagnetic correlated in the ordered state, they have an anti-ferromagnetic interaction. So it's basically a completely happy and certainly not a frustrated magnet at all. It's just gone into a wonderful arrangement of all the exchange interaction that allows it to go deeply into an ordered state. So basically, what we think is happening is that we have a highly frustrated spin system in the paramagnetic insulator, and in fact you can trace it to the honeycomb lattice with competing near and next near neighbor interactions, and it's extremely short correlations exist there. When we then cool it down, the lattice basically gives way. This is a really high energy phenomenon, and the lattice is saying, let me just distort a little bit, and I'll be able to adjust all of the exchange interactions so that I can now satisfy the interactions. I get a long-range ordered magnet, coherent magnetic excitations, and so this is actually kind of a structural relaxation to relieve the frustration. So the point basically that I'm trying to make is that we have, in this part of the phase diagram, in this material, we have a highly frustrated spin system. And perhaps that is part of why the Mott transition actually rears its head, in a sense, is that the system is not able to achieve magnetic order because of that frustration. And so, therefore, it's possible to have this exposed associated with that Fermi wave vector. And then eventually, when you, if you cool the system down, you have to go all the way out here. Then these correlations, which are related to a nesting kind of instability, eventually actually give rise to a spin density wave, and these are very sharp. And at this point, you're kind of dominated by the correlations imposed by the fact that you're in a metal. So our impression is that somehow the materials that do show this phase boundary happen perhaps to be highly frustrated, and that's our impression. And then I wanted just to conclude. That's what I basically was just mentioning about V2O3, and then in the to connect it to what I was saying about the spin liquids, we think that that's actually a very good place to look for spin liquids. That we in fact should be looking close to the Mott transition, and there are ways that you can argue for that as well, because proximity to the Mott transition tends to induce longer range interactions, because you've got the fluctuating charge allowing you to extend the range of the interactions, and that may in fact help to build fluctuations into the spin system. And then just the perspective is pretty dominated by our work on the scattering. I just wanted to basically say that there's quite a lot of progress now with the sources and the instruments, but I think where most of the science is actually going to come out is when we can collaborate more, the theoretical community, the scattering community. We're getting to the point we can measure these complicated patterns of scattering, but we don't actually have a theory to be able to think about it, and we cannot. There's some qualitative lessons you can take, but we really need, I think, to get better both at being able to measure these very broad continua of scattering, and also to have theoretical work that can actually account for that. Okay, with that, thank you for your attention.